Hello everyone, this is Professor Ng Chi Kun from Limas. In this video, I'm going to give you a lecture on approximate analysis of statically indeterminate frames with vertical loads. Building frames often consist of girders that are rigidly connected to columns. So girders are the horizontal members in a building frame, and columns are the vertical members in the building frame. So we assume that these girders are rigidly connected to the columns. This is to allow the structure to better able to resist the effects of lateral forces. One technique would be to consider only the members within a localized region of the structure. This is possible if the deflections of the members within the region cause little disturbance to the members outside the structure. So what this means is, we may consider a girder and analyze it as if the deflection does not affect the deflection of the outside structures. So we may take this girder as an individual member, another girder as individual member, so on and so forth. So the approximate location of the points of inflection can be specified, and these points are subjected to zero moments. So inflection points are the points where the positive moment changes to negative moment and vice versa. So therefore these points have zero moments. Let's look at this particular girder that is connected to two columns like this with uniform load. So the column supports at A and B will each exert 3 reactions on the girder. So in this case, what it means here is that if you want to analyze this girder, then we have to cut across the girder here and here and isolate the girder as a free body diagram for the analysis. So what we're going to get is something like this. The uniform load that is originally on the girder must be there with magnitude of W downward. So if we cut across the girder like this, then we're expecting 3 reactions at each of the cut section. So same as for this side of the girder. And then the girder is having a span of L. So in this case, in the free body diagram, we have 6 reactions which are unknowns. And for every free body diagram, we have only 3 available equilibrium equations. So meaning that there are more unknowns than the available equations. And we have 3 more unknowns more than the available equilibrium equations. So that's why we say that this girder will be statically indeterminate to the 3rd degree. So therefore we have to make 3 assumptions in order to do the analysis of this girder by just using the 3 equilibrium equations. So before we make the assumptions, let's look at what will happen to the structures at the 2 extreme cases. So in the first case, we assume that the columns are extremely stiff and there is no rotation at support A and B. So A is a fixed support and B is another fixed support. So the support cannot rotate when it's fixed. Therefore, we will get the deflection curve of this structure like this. So there is a change in moment sign at these inflection points here. So these are the points of zero moment. So for the case where the columns are extremely stiff, then the inflection points will occur at 0.21 L away from the support, from support A and also from support B. So that is the first extreme case. The second extreme case that we may look at is that we assume the columns are very flexible. So if the columns are very flexible, then we say that the column will rotate whenever there is a load. So meaning that there is a zero moment at the supporting columns, okay, as well as at, in the beams as well. So in this case, the zero moment points are at the support. So this is another extreme case that we assume that the column is very flexible. Okay, so in this case, the zero moments will occur at the supports. But in reality, the columns will provide some flexibility at the supports. It is not extremely rigid, no, it's extremely flexible, it's in between. So meaning that it's in between these two cases. In this case, the zero moment point is at 0.2 L away from the support. This case, the zero moment point is at 0 L from the support. Okay, so if we take the middle of these two extreme cases, then we might say that the inflection point or the zero moment points is at 0.1 L from each support. So with this assumption, we may simplify the analysis of the girdle. So in this case, we say that we need three assumptions from the beginning. So we said that we have three extra unknowns more than the available equation. So we have to make three assumptions. So these three assumptions are: number one, the first assumption is that the zero moment in the girder occurs at 0.1 L from the left support. So we assume that there's a pin at 0.1 L from the supporting column. And then the second assumption is that there's a zero moment point in the girder, 0.1 L from the right support. So this is the right support, and then the zero moment point or the inflection point occurs at 0.1 L from the right support. And then thirdly, the third assumption is that the girder does not support an axial force. So if the girder does not support axial force, then the horizontal reactions must be zero. So there is no horizontal reaction. So this should be zero, and this should be zero. So in this case, because this horizontal reaction will exert axial force in the girder. So we say that there is no axial force in the girder, there is no horizontal reactions. So this is the third assumption. So we have the first assumption saying that we have a pin at 0.1 L from the left support, and then we have a pin from the right support, which is also 0.1 L from the support. So these are the three assumptions. So first assumption, second assumption, and the third assumption. So in the end, we may idealize the structures like this. So we have a simply supported beam at 0.8 L of span, and then we have another cantilever beam which is 0.1 L and is fixed at the supporting column. So this is also fixed at the supporting column. So let us look at this particular example here on how to use the approximate analysis to get the bending moments and also support reactions. So in this case, you are asked to determine approximately the moment at the joints E and C caused by members EF and CD of the building band. So in this case, we have girder CD and girder EF at another level. So in this case, when we want to analyze this particular structure, we have to make use of the three assumptions that we have just learned in the previously. So this shows the idealization of the structures. So this girder is divided into three parts. So first part is a simply supported beam section where the span is 0.8 L. So L is 5 meters, so 0.8 L is 4 meters. So take note that this is similar to this. So we don't have to do two analyses. We do one and then it represents the other. And then in this case we have another cantilever part here and another cantilever part here, which is at 0.1 L from the support. So 0.1 of 5 meters is 0.5 meters. So first of all, we look at the simply supported beam part, right? So this simply supported beam is 4 meter length in span. Okay, so 4 meter. And then we have a uniform load initially. Don't look at this 64 kilonewton force first. We just look at this uniform load initially. And then for this simply supported beam, there should be vertical reactions at the pin joint there, and supposedly there should be a horizontal reaction, but we assume that this girder does not support axial force, so the horizontal reaction is 0. And then for the rocker support here, we have a vertical reaction. So these two are actually unknown reactions in the first place. So to solve for these reactions here, we have to convert this uniform force into a resultant force. So the resultant force is 16 kilonewton per meter length times 4 meters. So that will give you 64 kilonewton resultant force. So since this beam has symmetrical loading and symmetrical support conditions, then we know that the reactions must be symmetrical as well. So meaning that this support will take half of the total load and this support will have to take the other half of the total load. so giving us 32 kilonewton reactions at both ends. Then they are outward for equilibrium for total downward force. So if you notice that this beam is actually sitting on this cantilever. So if this beam is sitting on this cantilever, the reaction in this beam here is provided by this cantilever. So meaning that any reactions that you get from this beam here, meaning that the reaction that you get from this beam here will become an action on the supporting element. So this is a supporting element, and then now we want to draw a free body diagram for this cantilever beam here. So we cut across a section here. Okay, so that will give us a free body diagram like this. So when we cut across a section here, there should be a support reaction there and a reaction moment over there. So these two values are not known in the first place. Take note that these two are unknown reactions in the first place. And then from this part of the cantilever beam, we know that this cantilever has to support the simplicity of the beam here. So meaning that the reaction from the simplicity of the beam here will become an action on this cantilever beam here. Okay, and then the span of this cantilever beam is 0.1 L, which is 0.5 meters. Okay, and then this cantilever beam here also supports part of the uniformly distributed load, the UDL here. So we have a UDL here initially. Don't look at this 8 kilonewton first. We start with the uniform force here, a UDL here, which is 16 kilonewton per meter. And then we have the total length of the uniform force as 0.5 meter. So 16 times 0.5, we get 8 kilonewton resultant force. So this 8 kilonewton resultant force will act at the centroid of the uniform force. So this distance should be 0.25 meter from the support here. Okay, so meaning that we get a resultant force at kilonewton here from the uniform force of 16 kilonewton per meter length multiplied by 0.5 meters. And then the distance of this resultant force to the support here is 0.25 meters. So initially this is an unknown force or unknown reaction. So if we sum total forces in the vertical direction, then and we take upward as positive, so positive of this force minus 32 minus 8 should be equal to 0. So meaning that this force is 40 kilonewton positive. So meaning that positive, the assumption that is going upward is correct in the first place. And then, as I mentioned just now, this moment is also an unknown reaction. So to get the magnitude of this unknown reaction, so we assume this moment is a clockwise moment in the first place. So to solve for that moment, we try to sum the moments about this point here. So we sum moment about this point here. So we have this 8 kilonewton force with moment arm of 0.25 meter. We have this 32 kilonewton force with moment arm of 0.5 meters. And then we have the unknown reaction. So 3 components there. So initially we don't know what is the magnitude, so we may just call this moment MF or MD. Okay, we just call this MF or MD. Okay, so to begin, we need to assume a direction for summing moment. Okay, so normally we assume anti-clockwise moment as positive for summing moment. So here we sum moment F, moment at joint F, and they should be equals to 0. So now I'm taking joint F as my reference. So I assume that this is point F. I assume that this is point F over here. So this point is F. Okay, so total moment at joint F here is equals to 0. So this total MF is different from MF. Please take note. Total MF is the sum of moment, and then MF is the reaction moment. So now we are taking anti-clockwise moment as positive. So this MF here or MD, okay, now we just take MF. We just ignore MD, okay, because it's the same. So this moment here is a clockwise moment. So clockwise moment is opposed to this anti-clockwise positive, so we have minus MF. And then the second component that we look at should be this 8 kilonewton force. So 8 kilonewton force has a moment arm of 0.25 meter to F, and this force will cause an anti-clockwise moment with respect to joint F. So anti-clockwise moment is positive in this case, anti-clockwise positive. So the magnitude is 8 times 0.25. Okay, and then the third component will be from this 32 kilonewton meter force. So this 32 kilonewton force has 0.5 meter moment arm to point F, and then it is an anti-clockwise moment with respect to joint F. So anti-clockwise moment, we take it as positive. So this is the magnitude is 32 times moment arm, which is 0.5 meter. Okay, so there is no other moment, so we equate this to 0. Okay, so from here, if we solve for MF, we will get MF equals to 18 kilonewton meter. So when you solve this, we are going to get MF is a positive value. So positive value meaning that the assumed direction is correct. Okay, so meaning that the moment is going in clockwise direction. So that will solve for the moment and the support reactions there. Okay, similarly we can we can also cut across a section here and isolate this as another cantilever beam that looks like this. And this is exactly a mirror image of this. So meaning that all these are opposite. The moment in this case is clockwise. So the moment here is anti-clockwise. Okay. So meaning that the moment at this joint here, or at this cross section here, is 18 kilonewton meter clockwise moment. So at the end, we are going to get a bending moment diagram like this. So how do we get bending moment like this? Okay. So this part of the bending moment comes from the simply supported beam. Okay, it comes from here. Okay, so meaning that if we plot the bending moment of this beam, then you'll be getting 0 moment here, 0 moment here, and maximum moment of 32 kilonewton meter over there. Okay, so we know that for uniformly distributed load, the maximum moment is WL square over 8. So W is 16 kilonewton per meter, L is 4 meter, so 16 times 4 square over 8, we will get 32. Okay, so that is the maximum moment at the midspan of a simply supported beam. And then this part of the bending moment diagram comes from here. Okay, so this is a cantilever of 0.5 meters, and then the moment reaction here is 0. Okay, so let me magnify this. Okay, so we have a cantilever like this. So this is 0.5 meters, and we have a 32 kilonewton point load here, and then we have a UDL of 16 kilonewton per meter length there. So if we plot the bending moment diagram, we are going to get a bending moment diagram like this. Okay, so this part is considered a negative moment in the cantilever beam. Yeah. Okay, so in this case, this is negative 18 kilonewton meter. Okay, so there is the moment here, and then the moment at the tip of the cantilever is 0. Okay, so this is at 0.5 meter. So therefore, we have a moment diagram like this from the cantilever portion of the beam. Yeah. Okay, so this is the inflection point or 0 moment point at 0.5 meters away from the supporting column. Same as for this side, which is symmetrical to this side as well. Okay, so thank you very much for listening. This is the end of the lecture. Thank you very much.